Welcome back to Algorithmic Game Theory. In the last lectures, we've learned a lot about mechanism design and particularly combinatorial auctions. And the kind of mechanisms that we were considering were always auctions of some sort, meaning that you, and every other player as well, submit a bid, and then based on what the bids are, the mechanism makes the allocation. But unless you're a professional art collector, this is not what your daily shopping experience is like. Usually, you just go to a store and then you see a posted price. So you see, okay, I can now buy this item for this much, or I can buy 2 items for just then double the price. And how can one capture these kinds of settings mathematically? And also, are those efficient in the way that do we come to a good outcome? Do we come to good social welfare this way? This is exactly the question that we will be considering today with some classical economic theory, and then also next time when we talk about a more algorithmic approach to this, which is more general but then also loses something. You will see the differences between these. But as I was mentioning, today we'll only consider classical economic theory, namely we'll get to know the concept of a Walrasian equilibrium. What is this? We have again n players or agents. You can also call them bidders, although they are not actually bidding. I often will call them just buyers, because this is what they are actually doing. And then we have m items. This is the set we call 1 through small m, and which we call capital M. And we're now in the standard setting of combinatorial auctions, so each player I has a valuation function Vi mapping from the power set of the items to the non-negative reals. So again, each player has a non-negative value for every subset of the items. But what is different now is that we consider full information, so these are public knowledge. We know these Vi, and also everybody else knows them. So our question today is not at all about incentives, letting these players reveal their true values. This is no question today. Rather, we are interested in the question, do there exist good prices? And whether or not there exist good prices, this is formalized in the concept of a Walrasian equilibrium. It's called a Walrasian equilibrium after Leon Walras, an economist who introduced this concept. How is this defined? A pair of a price vector Q and an allocation S, which is a vector of S1 through Sn, each Si being a subset of M, and sets that are pairwise disjoint. So each item is allocated to at most one player. And this we now call a Walrasian equilibrium. If two conditions are fulfilled. The first one is that Vi of Si minus the sum of all j and Si pj, this is at least Vi of Si prime minus the sum of all j and S prime Qj, and this should hold for all Si prime, which are subsets of the items. And then we also have the condition that if an item is not in the union of all Si, then its price has to be 0. Good. Let's have a closer look at this. We see a Walrasian equilibrium is nothing like the kind of equilibria that we've seen so far. For example, a Nash equilibrium. A Nash equilibrium was always about each player choosing a strategy and no player wanted to unilaterally deviate from this. Here now players are actually not choosing any strategies, but still it is kind of formalizing the intuition that every player should be happy with their allocation and the prices. And this is as follows. So a Walrasian equilibrium now consists of this price vector and also the allocation of the items with the following properties. Let's say I'm player I. I'm now getting set Si. And then I'm paying the sum of the Qj for the items in Si. Am I happy with this? Yes, I am happy with this, unless there is another set Si prime for which my value minus what I would have to pay for that is higher. And this is written down here. So this would be my quasi-linear utility if I'm getting set Si and I'm paying the sum of the prices in the set Si. And this is now for the set Si prime, what would be my value minus what would I have to pay. And this condition now tells us that every player should be happy with what they are getting. So I forgot to write this down. This should, of course, also hold for all players. So no player is unhappy with what they're getting. No player would rather get a different set of items than the one that they are currently being assigned. And then there's this other condition, which is as follows. If an item is not allocated, then it should certainly have a price of 0. This is maybe a more technical condition, which will turn out to be useful later. But the point is that if nobody is getting an item, then it should have a price of 0. So it should be, and this then combines with this first constraint, it should be easy to get. So if there is an unallocated item, then I shouldn't be made happier by giving me this item on top, because I could, for example, include in Si prime everything that I'm getting so far and everything that is not allocated. Then I would still pay the same, and this should make me happier. So this kind of means that items which are not allocated are worthless to some extent. Let's see a very simple example of such a Walrasian equilibrium. Namely, let's first talk about only a single item. And let's assume that the value of player 1 for this item is bigger than the value of player 2 for this item, and so on. So the players are ordered by decreasing value. Now, all Walrasian equilibria are as follows. We'll have a price somewhere between V2 and V1 for the item, and player 1 is getting the item. Why is this a Walrasian equilibrium? Let's verify these inequalities or these conditions. The second condition, this is certainly fulfilled because the item is allocated. Good. Why is this first condition fulfilled? Let's first consider player 1 who's getting the item. Then this will be the value of the item for this player. So this will be V1, and we subtract the price from it. So something between V2 and V1. And this will always be non-negative. Cool. What's the alternative? The alternative is not getting the item. And not getting the item will give us 0 minus 0, so that then we'll have 0 on the right-hand side. Okay, so we have something non-negative is at least 0. This is exactly what we're asking for. Now let's consider one of the other players who are not getting the item. There, of course, this thing here is 0. They're not getting the item. And how big is this? Well, they could get the item, but how much would they have to pay? They would have to pay the price, which is somewhere between V2 and V1. The value would be something like V2, V3, or whatever, but it would be at most V2. So we'll see V2 minus something that is at least V2. So this is something non-positive here on the right-hand side. So also this inequality would be fulfilled for these players. You can now also verify that there are no other Walrasian equilibria. And indeed, we'll do this in a little more general way after the next example. But before that, let's see a more complicated example, namely where we have multiple items. So we might also consider unit demand valuations. We've come across them a number of times now. Vi of Si would be the maximum of all j in Si, Vi, j, for Vij being non-negative. What does this mean? This means I only want at most one item, or more items don't make me happier. We can now think of this as follows. We have, for example, these 3 buyers, and we have 3 items. And generally, we could now give each of the buyers, maybe we could even give all 3 items to buyer 1. But the thing is, giving them all 3 items doesn't make them any happier than getting only one of the items. So this is why we can think of this as a maximum weight matching problem, which would look as follows. So I'm now drawing only the edges in which a buyer has a non-zero value for the respective items. And then, for example, buyer 1 might have a value of 10 for the first item, no value for the other items. Buyer 2 might have a value of 5 for the first item and a value of 3 for the second item. Buyer 3 might have a value of 2 for the second item and a value of 1 for the third item. Now, how do we find a Walrasian equilibrium here? What is a Walrasian equilibrium? A Walrasian equilibrium is, first of all, an allocation of the items, which might now be the following. Give the first item to the first bidder, the second item to the second buyer, the third item to the third buyer. And then we also have to set prices. And we could now set the first price to 3, the second price to 1, and the third price we could set to 0. And then we can again verify that everybody is happy with this. Buyer 1 pays 3, gets a value of 10, so we'll have a quasi-linear utility of 7. What would be the alternatives? For example, getting both items B and C, just to mention one example. Then the value would be 0, but the sum of the prices would be 1. Or, for example, getting item C alone, this would make give a value of 0 and also a price of 0, or not getting anything, then we get the same. And now if you go through all three players and any possible set of items that they could get, you will realize, okay, they won't be any happier than they are now. And what is interesting about this is that this is exactly the VCG allocation and the VCG prices. If we were running VCG, this would be the allocation that would come out, and we would then see, okay, how much does this buyer have to pay? Well, what would be the alternative allocation? Instead of this horizontal one, it would be these diagonal edges. And then we would see, okay, we would indeed have a VCG price, a VCG payment of 3. This is a connection that we'll also see later. But there's also an alternative Walrasian equilibrium, which uses higher prices. The first price could be 10, the second price could be 3, and the third price could be 1. Now, still everybody's happy, although, for example, buyer 2 has a value of 3 and also has to pay 3, so the quasi-linear utility would be 0. And this is indeed true for all three of them. However, whatever other set they could be getting still would make them happier. Good. So we see that usually the Walrasian equilibrium won't be unique. There seems to be something related to VCG, which we'll have to explore. But it seems that often a Walrasian equilibrium exists. But not always. There are valuation functions for which there is no Walrasian equilibrium. For example, the following. V1 has a value of 1 if the player is getting the first 2 items or any superset of this. Otherwise, it will be 0. Similarly, for the second player, we'll have a value of 1 if this player is getting items 1 and 3 and no value otherwise. The third player will have a value of 1 if they're getting items 2 and 3 and no value otherwise. And now you can figure out that there is no Walrasian equilibrium. Why is that true? Well, now you have to distinguish what the allocation might be like. And indeed, you might, for example, give items 1 and 2 to the first bidder and no items to the other two. That would be one alternative. And let's see why this won't lead to any good price vector. So we have no Walrasian equilibrium. For example, there are no prices to support the allocation in which S1 would be the set of items 1 and 2, and S2 and S3 would be empty. Why is this? Well, let's recall what the prices would have to fulfill. First of all, item 3 isn't allocated. And because item 3 is not allocated, it has to have a price of 0. What else do we have to have? Players 2 and 3 have to be happy with what they're getting, namely they're not getting anything. But what would be an alternative for them to what they could get is for the second player, we could also give them the set of items 1 and 3. And for the third player, we could also give them this items 2 and 3. So what has to hold? V2 of the empty set minus the sum of the prices in the empty set. This has to be at least V2 of items 1 and 3 minus the sum of the prices in 1 and 3. And what do we have now? This would be 1, this would be 0, this would be 0, and this would be just the first price because Q3 is 0. So what we're getting is that Q1 has to be at least 1. And analogously, Q2 will have to be at least 1. But this now means that player 1 will be unhappy, because if we now give items 1 and 2 to this player minus the sum of the prices, this will be the value minus the sum of the prices, which is Q1 plus Q2. This will be negative. And this will be this way smaller than if we gave them the empty set. And this is a contradiction. So you see, this certainly will not be a Walrasian equilibrium, and now everything else that you might want to try here, you will reach to the exact same problem. There won't be any prices for whatever allocation you try. So there is just no Walrasian equilibrium. This is for a good reason, and there's a lot of theory around this, which often relates to duality of linear programs. But for today, we'll only see that there is always a Walrasian equilibrium for unit demand valuations, and also that a Walrasian equilibrium always maximizes social welfare. The first result that we will be proving now is the first welfare theorem, which states that Walrasian equilibria are always socially optimal, meaning that they maximize social welfare. Let's write this down. If Q, S is a Walrasian equilibrium, then S maximizes social welfare. This result is often referred to as markets are efficient because it says there is a way. No, it doesn't actually say this. You can, if you have a not so close look at this, then it says however you set prices, you will end up in a state that maximizes social welfare. Although this is not quite true, because as we've seen, Walrasian equilibria not necessarily exist. And so this only is meaningful if Walrasian equilibria do exist, because then it says that there is a way to set prices such that social welfare is maximized, and also any other way that you could set prices and everybody's happy, that will also maximize social welfare. Although it doesn't state why the world should end up in this state. Good. Regardless of all this meta discussion about this theorem, let's prove it. Let S star be an allocation that maximizes social welfare. Then, in our Walrasian equilibrium, every player is still happy with what they're getting, and they wouldn't rather want to get what they're getting in this allocation S star. So we can write this like this. Vi of Si minus the sum of j in Si qj, this will be at least Vi of Si star minus the sum of the prices in Si star. Good. This is just the property, the first property of the Walrasian equilibrium, that everybody's happy with the set of items that they're getting. Now what we can of course do is we can sum up this inequality over all buyers. What will this look like? We are now getting the sum of all vi in S, vi of Si minus the sum of all I in N, sum of all j in Si, Vj. This will be at least sum of all I in N, Vi of Si star minus the sum of all I in N, sum of all j in Si star, Qj. Good. What do we now know about these sums here? What do we know about this sum? This is a sum over all players and then over the set of items that they're getting, summing up all the prices. Which items are we summing over? We're summing over all items that are allocated, and each item that is allocated appears exactly once. And what about the items that are not allocated? Well, they don't appear here, but we know that Qj will be 0 for them, because this is a Walrasian equilibrium, and this was our property. So we'll see that this is exactly the sum of all item prices. Now, this thing here, this will be at most the sum of all item prices, because also here, every item is appearing at most once, because it is a feasible allocation. Now here, we don't have this as equality, because there might be items that are not allocated by S star, but which have a non-zero price, because Q was just the prices that work well with S, not necessarily with S star. If you now combine this, then what you see here is that still the sum of the Vi of Si will be at least the sum of the Vi of Si star. And this is exactly what we were claiming, namely that social welfare is maximized. Fantastic. And it's this easy to prove. If you're familiar with duality of linear programs, this might look a little familiar, because this is indeed exactly LP duality for one specific LP, namely the configuration LP. And as a matter of fact, everything about Walrasian equilibria is more or less LP duality. Sometimes it is strong LP duality. But if you don't know LP duality, doesn't matter for now. All you have to see is that if there is this Walrasian equilibrium consisting of an allocation and prices, so that everybody is happy with this allocation giving these prices, then this allocation has to maximize social welfare. And this is the entire argument. But this, of course, doesn't tell us that there always is a Walrasian equilibrium. And as we've seen, sometimes there is no Walrasian equilibrium. And this is what we want to do next. We want to show that for unit demand valuations, there is always a Walrasian equilibrium, and we will be able to see that this corresponds to the VCG outcome. In our example of a Walrasian equilibrium, we saw that this Walrasian equilibrium corresponded exactly to the VCG outcome. one of the two Walrasian equilibria that we saw in this example. And indeed, this is a very general property, namely that if all valuation functions are unit demand, then the VCG outcome indeed corresponds to a Walrasian equilibrium. Before we can prove this, maybe we first have to recall what actually VCG does. And we might also want to change notation a bit here because we're talking about a very specific setting, and this will simplify our proof. So we'll have unit demand valuations, which means that Vi of Si will be equal to the maximum of all j and Si, Vi, j. And how did VCG work? Let's call S a welfare maximizing allocation. The valuations are fixed today, so we don't actually have to care about all this, what actually mattered for us in the context of VCG, namely that this is truthful. So S will be just a social welfare maximizing allocation, and SI prime, SI superscript minus I, this is a social welfare maximizing allocation if bar I is excluded. And then we'll have that the VCG payments are as follows. So everybody bids truthfully. And we now say, okay, take the social welfare that you're getting when you're doing everything without bidder I minus the social welfare that you're getting if you include bidder I, but not count them. So once again, here we are taking this allocation S minus I, in which bidder I is excluded. We are not counting them, but just maximize social welfare without them. Here we include them, and in both cases we only sum up the values that all players except for player I have. And the thing is now, every player will get, well, technically they can be getting multiple items, but they're getting more or less one item. And if we now use these as the prices, then this will correspond to a Walrasian equilibrium. More precisely, what we can say is that we now define item prices by as follows. If J is not allocated, in S, then we'll set the price of item J to 0. if J is allocated to buyer I, then we'll set Qj equal to whatever buyer I is paying, and this is again given by this VCG formula. What tends to make this a bit confusing is that here we are assigning payments to the buyers, and now we want to assign payments to the items. As I was saying, okay, actually every buyer gets at most one item, but we'll even do this in the most straightforward way. So even if a buyer gets multiple items, then we assign as the price whatever this buyer is paying in the VCG outcome. And now we claim something very simple, namely we claim that S, Q is a Walrasian equilibrium. So what this tells us is that, apart from the nice fact that this construction is a Walrasian equilibrium, it tells us that, first of all, there is a Walrasian equilibrium, because so far we've only seen examples of Walrasian equilibria, but we've also seen an example where no Walrasian equilibrium exists. So what will we have to verify? We'll have to verify that via this construction, the properties of the Walrasian equilibrium are fulfilled. There's this thing that is already great, because what did we insist on in the Walrasian equilibrium? That items that are not allocated have a zero price, so this is by design. But is every player happy with what they're getting? We don't know yet. Everything that we've shown so far regarding VCG was about truthfulness and truthful reporting, but this is not the point today. We assume that we just know the values in this entire construction. So today is not about lying, but it is about just making everybody happy. So is everybody happy or not? How do we prove this? The first thing that we do is we'll understand how these prices are constructed. How is such a price Qj actually defined via this construction? Okay, it is defined in some way, but we'll now define, or we'll see that this is actually, there's an equivalent way which just talks about adding and removing items rather than adding and removing bidders. And this is as follows. We have that for every item, the price can be also written as follows. Take the sum over all buyers. What is the value of some allocation A superscript plus J minus what is the value that they're getting in allocation S? And what is S plus J? S plus J is a social welfare optimizing allocation when there are two copies of item J. Good. So originally we defined the price by saying, okay, who's getting the item? And then what's the VCG payment for this bidder? Because, well, this then means remove this bidder, let's see what social welfare are we getting without this bidder, take the difference between how much we're getting with him or without him. So how much does he or she hurt the others? Now this is a different way of stating this. Now we state that the price of item J is what by how much our social welfare would increase if we had item J twice rather than once. So this is again our social welfare if we have each item once. This is the social welfare where we have all items once except for item J, which we have twice. And the interesting thing is this is an equivalent way of stating the VCG payments. Why is this true? This proof relies on actually two properties. The first one being if J is not allocated in S, neither copy is allocated in S plus J. Is this surprising? Not really. Why that? Because we now have an allocation S, which has each item only once. Now we're giving this allocation another copy of item J. But before, item J wasn't even used. Now we'll have another copy of this item J. So now we have two items J. But why should we now start using them if before we didn't actually care that we had one copy? And then the other property is that if J is allocated to bidder I in S, bidder I also receives one copy in S plus J. Is this second property, is this surprising? It's maybe a little less intuitive, but I don't consider this surprising. So we now have this allocation in which we have each item once, and now bidder I is getting item J. And now we're getting another copy of item J. What will happen now? Will it happen that suddenly both of these item copies are going to somebody else, or will bidder I keep at least one copy and then the other copy is going to somebody else? Or maybe it's even unallocated. This sounds very reasonable because, and that's really important, each bidder will get actually only one item in the optimal allocation. How do you prove such things? Those are actually fundamental properties of bipartite matchings. So let's maybe see why this first property is true and how you would formally prove it. So if item j is not allocated in S, then neither copy is allocated in S plus j. The first thing that we could see is that if only one copy is allocated in S plus j, then we could also use S plus j as S. And now I realize I forgot to mention something, namely, we say that S plus j is only different from S if it gives a strictly higher welfare. So this is always an issue of tie breaking. But here we now say, okay, we call, in this case, if only one of the two copies is allocated, then S plus j cannot give higher welfare than S, because we could just use whatever S plus j is doing also in S. And this means that by our assumption that I forgot to mention earlier, S plus j and S have to be equal. And this already shows us for this first case, if S plus j uses only one of the two copies, then S could just do the exact same thing. So the only interesting case is that actually S plus j is using both copies, and we will now see a contradiction that S isn't using at least one of them. How do we show that? Well, let's think of this a little more visually. We'll have a couple of buyers and we'll have a couple of items. Now there's of course item j, which we have twice in j plus 1, so this will be item j. Let's now first draw our allocation S. And once again, allocation S does not use item j. So this might look like this. They are using these items, they're getting these items. And now let's consider allocation S plus J. Well, now suddenly there are two who are getting actually item J, and then the other items are allocated in some other way. Of course, not this way, but rather this way. Good. So, once again, these lines indicate our allocation when there's only one copy of J, what would maximize social welfare, and we're not using item J at all. And then suddenly there's another copy of item J, and we then have a different allocation, and both copies of item J are used. So both these and this player are now getting item J, whereas before they were getting something else in allocation S. But what does this mean? We now have an alternating path that corresponds to the reallocation of the items. This item was first is now allocated to this buyer who before got this item, and this item was before allocated to this buyer, and so on. And now this is exactly the alternating path that we're getting here. And the same is true for the other item copy. And what we're seeing here is that those are two disjoint alternating paths. And the point is now, if this increases social welfare, then one of the two, so either this part or that part, will also have to increase social welfare. Which means it cannot be a good idea to not allocate item J at all in S when suddenly it is allocated twice in S plus J. Good. Now I won't go into further details on this because I hope also that these two properties that I claimed here, those aren't too surprising. So you now see the general kind of argument that you can use to prove these properties. But what was it that we actually wanted to show? We actually wanted to show that the prices that we constructed from VCG have exactly this form, so we can also write them like this. We can write the price that we're giving to item J exactly like the social welfare of the allocation the social welfare maximizing allocation when we add a second copy of item J minus the social welfare if we did not add a second copy and still maximize social welfare. Good. Now, how do we show this? Let's consider first the case that item J is not allocated in S. What does this property tell us? If J is not allocated in S, then neither copy is allocated in S plus J. So S and S plus J have to be identical, and then the price will be 0. Good. So this is exactly what we before set our price to be if it is not allocated in S. Then there's now the other question, what happens if item J is allocated? If item J is allocated to buyer I in S, then what will Qj be? Qj will be the sum of all I prime, which are not equal to I, via subscript I prime of S I prime minus I. Once again, this was how we defined the prices via VCG. And what do we now know about this? Maybe let's go back to the properties that we have. If item J is allocated to bidder I in S, this is the second property, then bidder I also receives one copy in S plus J. What does this mean? That everybody except for bidder I is getting just something in S plus J, because bidder I is getting S plus J and the other bidders get whatever is remaining, because we now just have exactly one copy of each item left. And this means that this S plus J is doing the exact same thing, because now bidder I is taking this one copy of item J. This is doing the exact same thing as if we were leaving out bidder I and then maximize social welfare. So introducing a second copy of the item that bidder I was getting is just exactly the same as removing this bidder from our allocation, or from our allocation process, and then maximizing social welfare. So So this now means that not counting, removing bidder I and not counting them, we'll get the same social welfare as if we considered the allocation S plus J. And I was a little imprecise here. We have to have the same social welfare, but if we're not counting bidder I. And so this is the precise formula for this. And what does this now mean? This now means that Qj, how big was this? This was exactly equal to the social welfare that we're getting if we are adding one copy of item J, and then we ask what's the social welfare of everybody except for bidder I minus the social welfare before counting everybody but bidder I. Now this, to add now bidder I, we can just add Vij on both sides. And what we'll see is that what we've now added is exactly what we're getting from bidder I. Cool. So this proves our lemma, which was what? This proves our lemma that for every item we can rewrite the price that we're getting from VCG as follows. We can write it as the social welfare of the allocation if we maximize social welfare with an additional copy of item J minus the social welfare that we're getting if we just do everything with a copy of each item only once. And now the only thing that we have to do is we'll only have to prove our theorem by this lemma, which was stating, okay, with these prices we'll get to a Walrasian equilibrium. How do we do that? For every item L, we have the following property that, of course, the item has a price which is defined as social welfare that we're getting if we introduce another copy of it minus the social welfare that we're getting without this, without introducing another copy. So in particular, we want to understand this term here. How big is the social welfare that we're getting if we introduce another copy of item L? For all players, we now have the following, that we might add another copy of item L. The social welfare we're getting will be at least social welfare if we give item L to bidder I, plus the social welfare that we're getting from everybody else, but now bidder I isn't getting anything. And this way, we of course get that QL will be at least VIL plus the social welfare that we're getting from everybody else if we're optimizing without bidder L, minus the social welfare that we're getting overall. Now, how much is this? This thing here, this is exactly the social welfare that we're getting from everybody except for bidder I plus their value. This is true if Si prime is equal to the set J. And what else do we know? What is it that is remaining here? What is remaining here, this is exactly the following: VIL minus Vij plus the difference of these two sums. And how big is this? This is the exact definition of Qj that we were starting from if bidder I is getting item J. So what we're getting here is that QL will be at least VIL minus Vij plus Qj, or equivalently VIL minus QL will be at most Vij minus Qj. And we're done. Why that? Because this is exactly the property that we wanted to verify. That if bidder I is getting item J in allocation S, then they don't want anything else better, meaning that their value minus what they have to pay for the item, this will be no more than the value minus what they pay for the item that they're actually getting. Cool. So I'm always a little confused by this proof because it assembles these inequalities in a strange way. Maybe there is a smarter way of writing this so that this feels more straightforward, but at least I haven't found that yet. Nonetheless, let's summarize here what we've done. We've shown that the VCG outcome always corresponds to a Walrasian equilibrium for unit demand valuations. For other valuations, this is not necessarily true. One of the reasons being there might not be even a Walrasian equilibrium at all, although VCG always works. And that's something you might want to verify, that also the VCG outcome gives payments which don't relate to a Walrasian equilibrium. Why that? Because one of the things being VCG always assigns a payment to each of the bidders, whereas the Walrasian equilibrium assigns item prices. And if you now have the setting where each bidder is getting multiple items, how would you now set the prices? That's not so clear, and that's why usually it won't work. Good. But beyond unit demand valuations, there are still sometimes Walrasian equilibria, namely there is a class of valuation functions called gross substitutes, which generalizes unit demand functions, which always admit a Walrasian equilibrium. And there's many more things that you can show. For example, you can show that here in this unit demand setting, any Walrasian equilibrium will choose prices which are at least as high as the VCG prices. Good, but we're out of time for today. So now we have an understanding of what the classical economic theory is like when they talk about existence of prices, and they have this first welfare theorem which tells them, okay, there are prices. No, that doesn't tell them, but it tells them that if there are prices in the Walrasian sense, then the market is efficient in the way that it maximizes social welfare. Next time we'll talk about a similar but different setting, because then we'll change some things. We will most importantly consider the incomplete information setting, where we don't know the valuation functions in advance, but we still want to set prices. Then we won't be socially optimal, but we will at least be provably close to this. So stay tuned for next time. Thanks for today, and please do let me know if you have any questions. Stay safe, have a great day. Bye.